Welcome back. So we were talking about the machine learning framework, right? So we talked about the training step. We talked about how we assess the performance of the model we learned during the training on new unseen data. We talked about different sorts of errors, right? So representation error, optimization error, as well as the empirical approximation error. Now in this lecture, I just want to talk about some basic examples that we use to basically solidify the machine learning framework. Okay. So, and these are very basic examples, right? And typically belong to the supervised learning category of machine learning, meaning that we have a collection of features and labels. Again, those could be images and their labels. And let's say we want to classify the images, right? So I have images of different digits, 0 to 9, and I want to learn a classifier that given a new image, it can tell me whether that image is basically 0, or is it 1, is it 2, etc. Okay? All right. So the first set of problems or models, if you will, is binary classification. So it's a simple classification problem where I have only two classes. Okay. So imagine that I have a class of plus, okay, and a class of minuses. Again, plus you can think of it that images of a car, and minus images that are not car. Okay. Now, the goal of the classification problem is to, as I said, learn a classifier, in this case a hyperplane, that can separate class plus from class minus. Okay? So what are the elements of this problem? We have our feature vector x, okay? Again, could be the collection of pixels. We have our labels, +1 and -1, so just two of them because it's a binary classification problem. And we make an assumption that the data is linearly separable. Again, there is a linear line, linear hyperplane that can separate the plus sign and minus sign. Therefore, a natural class of models is basically models of the following form, right? So they look at basically the inner product between x and w. So w is basically the normal to the hyperplane. And if that inner product is positive, we say that, hey, this image belongs to the positive class. And if that inner product is negative, we say that that image belongs to the other side, to a negative class. Okay? So we just look at the sign of the inner product, right? So that's our models. So it is essential to talk about loss functions when we want to perform training. So in this example, we typically deal with two loss functions. The first loss is 0-1 loss. Okay? So this essentially assigns a value of 1 if the model is not able to fit the IS data. Okay? In particular, if it misclassifies the IS data, and otherwise it assigns a value of 0. So if my model is able to classify the, let's say, the IS image in my training data correctly, there is no loss. If it classifies it incorrectly, I incur a loss of 1. Okay. Now, this is very intuitive, and another reason that this is a useful loss is that when I talk about the average loss, or basically the loss of a sample z, and by the way, this is basically the indicator function. Okay, so it returns a value of 1 if the argument is true. Otherwise, it returns a value of 0. So it's not difficult to see that if I take the expected value of this quantity over the choice of z, this is just going to be the probability that I misclassify the ith sample. So the average loss in this case is nothing but the probability of misclassification. All right. Now, although this is very intuitive, one issue with that is that it's going to make the training difficult. We talked about convexity and the fact that convex functions are nice and can be optimized efficiently. The issue with this 0-1 loss is that it's not going to be, it's not going to lead to a convex optimization problem. Therefore, what we typically do is to replace this loss with the best convex approximation that we can design. And that approximation is called the hinge loss. Okay? So hinge loss is nothing but an approximation to the 0-1 loss, and it takes the following form. Okay, so the max between 0 and 1 minus the inner product between x and w. Okay. As I mentioned, the nice thing about this is that the empirical risk minimization problem, basically the training problem, is going to become a convex task, meaning that we can efficiently solve it. Okay. So the convexity of the learning task depends on two key properties. The first one is the hinge loss, the use of hinge loss that I mentioned. And secondly, it depends on basically this linear hyperplane model that I'm adopting as my classifier. Okay. Now, this linear model is useful when the data is linearly separable. But if I give you an example where the data is not linearly separable, let's say I have 1 minus here, something like this, where the positive class is surrounded by the negative class. This is not a linearly separate model. So this is not a linearly separate problem. Therefore, the linear hyperplane is not going to be a really good classifier for this case. So what we can do is to replace this simple linear relation with something more complicated. For instance, we can replace it with a deep learning model, a highly nonlinear model. Okay, that will typically increase the representation power of our model, but the catch is that it's going to result in a non-convex training task. Okay, so that's the first example. The second example is called linear regression. Okay. So in particular, you can imagine that I have a bunch of data points that are very well represented with a linear model. Okay. And my goal is to leverage these data points to learn this linear relationship. Okay, so what are the elements of our problem? Again, we have our features. X is a collection of features, okay? So in RD, the labels now could, in general, be real valued, okay? So they're not necessarily +1 or -1, okay? We also assume that, as I mentioned here, the relationship between the features and labels is typically following a linear model, meaning that the label is just the inner product between x and some unknown parameter w that we hope to learn, we hope to find it by leveraging some data points. Okay. Sometimes we also include a noise term. Okay, so basically the labels that we see are noisy. Okay, so they don't always provide the correct label, but the noise is small and manageable, such that if we leverage our training data, we should be able to to learn this relationship hopefully very easily and efficiently. Okay, so what's the other element that is of essential to talk about? That's nothing but the loss function. Okay, which losses are we going to use to fit our model to the training data? And typically in linear regression, we use the square loss. Okay, so again we capture how well we can fit a specific sample xi and yi by looking at the square loss. Now the nice thing about this problem is that, again, if we use a linear model and if we use the square loss, the empirical risk minimization problem is going to become a convex task, which basically means that we should be able to solve it very, very efficiently. But again, one drawback here is that the relationship may not be as nice as linear as I'm depicting here. For instance, I could have a highly nonlinear relationships. So obviously, my linear model is not going to be a good fit, but a nonlinear model, such as this one, is going to be able to fit the data much, much better. Okay? And we can do this in practice by replacing this simple linear relationship with a much more complicated and nonlinear model, for instance, using a deep learning architecture. And the catch is that this is going to typically be a non-convex training task. All right, the third example is also a classification example, but for historical reason, it's called regression. Okay, but in fact, what we are doing, we are performing binary classification. And that's the problem of logistic regression. Okay, so in particular, what we are assuming is that, let's say we have some, again, positive class, and then a negative class here, such that I can use like a S-shaped model, if you will, to classify them. Okay, so this side are all plus, and this side are all minuses. Okay, so therefore the goal is to learn the specifics of this S-shaped model. Okay. All right, so what are the elements of the problem again? We have features. Again, these could be collections of pixels of an image. Okay. We have labels. We can use +1 and -1, or we can use 0 or 1. It doesn't really matter much. So here I'm using 0 or 1 to denote the two different classes that I have in this problem. And we are sort of assuming the following relationship between the features and labels. We are assuming that that could be represented by a sigmoid or logistic function or activation. So this S-shaped model that I talked about is essentially captured with this relation. And this is called the sigmoid function or logistic function, which is very, very important in machine learning and deep learning. The way to make sense of this is to think of this quantity, 1 over 1 plus the exponential, as the probability that the label of x is 1. So this quantity, which incidentally is always between 0 and 1, is going to say the probability that x is, the label of x is equal to 1 or not. So if this is very, very large, then it means that it is very likely that x belongs to the class of 1s. For instance, x is very likely that x is a car, the image of a car. On the other hand, if this quantity is very low, near 0, that means that it is unlikely for x to be an image of a car. Okay? So therefore, it belongs to the other class. Now, a natural loss function to optimize here is called the binary cross-entropy loss. Okay. This in some sense captures the difference between two distributions, if you will. Okay. And this is something that we're going to talk about it a little bit more when we talk about classification again, but in the context of deep learning models. But in some, again, so the way to think of this is that that this is a notion that captures the distance between two distributions. In particular, if I leverage this during my training process, this is going to learn a model that can very well fit the training data that I have. Meaning that, ideally, if the training is done successfully, this is going to return a value which is very, very close to 1 or even 1 for all the examples that I have in the training data that belong to the first class, and it's going to return a value which is 0 or very, very close to 0 for all the examples that I have in my training data that belong to the other class. Okay. Now, again, like the other two examples we talked about, this is going to lead to a convex optimization problem. So our training problem is going to become a convex problem and could be solved very, very efficiently as long as we, again, use this specific way to represent the relationship between the features and labels, and as long as we are leveraging the binary cross-entropy loss. Like the previous two examples, in practice, this is not going to be powerful in many cases in representing, again, the relationship between the features and labels. So what we tend to do is that we replace this linear relationship with something more complex and nonlinear, such as a deep learning model. And that will result in a non-convex training task. Okay. Now, one question here that we may ask is that, okay, these examples are simple, so we may not be able to leverage them in practice, right? So then why are we talking about them? And the reason for that is that this gives us the way to talk about the process of applying deep learning models. In particular, you can think of deep learning as finding a much, much better representation of the original training data. In particular, I have the original features, let's call it X. Maybe if I just look at X, I'm not going to be able to, again, crack the learning task. But if I have a very powerful deep learning model, what I can do is that I can feed this image, let's say, into a deep learning model, and instead I can find a much, much better representation of the input image. I can extract very, very useful features from that image, such that if I feed this to one of these examples we talked about, let's say linear regression, logistic regression, which depends on, again, whether you're talking about a regression problem or a classification problem. After finding these useful features, extracting these useful features from the data, thanks to leveraging a deep learning model, you should be able to perform very well. Okay, so therefore, despite the simplicity of these models, there are still a lot of useful concepts that we'll be leveraging when we talk about learning problems in the context of deep learning. Notably, the loss functions that we introduced here, these relations that we talked about here, such as the sigmoid functions, sigmoid activations, are something that we're going to build upon when we, as we are progressing in this course. So that's basically the end of our lecture on the basics of machine learning procedure. In the next lecture, we're going to start talking about some of our training algorithms. Notably, we're going to talk a little bit about the gradient descent algorithm. I'll see you next time.